In this video we are going to look at a heat convection problem that's going to give us some insight about what happens when you have different fluids and you have the heat convection and there is heat exchange between the moving fluid and a surface. So without further ado, let's solve this problem. So let's start with the problem statement. It says that there is a square isothermal chip piece of width W equals 5 mm on a side that's mounted on a substrate such that its side and back surfaces are well insulated, while the front surface is exposed to the flow of a coolant at T equals 15 degrees Celsius. And there is a constraint which says that from reliability considerations, the chip temperature must not exceed 85 degrees Celsius. So we have to keep that in mind when solving the problem. The question asks, if the coolant is air and the corresponding convection coefficient is H equals 200 watts per meter squared Kelvin, what's the maximum allowable chip power? Then the question again asks the same thing, except that it says that if the coolant is a dielectric liquid for which H is 3000 watts per meter squared Kelvin, what's the maximum allowable chip power? So let's draw a sketch of the problem. So this is our chip. It's a square chip. So one of the sides of this chip is 5 millimeters. So that's the distance. From this we can actually calculate the area of this surface, the top surface, and the area is going to be 5 times 5 millimeters squared, or we can write it with 25 over 10 to the power 6 meters squared if we convert it to SI unit. Since the question says that there are no heat transfer from the side and back surfaces, so that's a critical piece of information, that the side and back surfaces are well insulated. So this means this surface which are side surfaces, and the back surface which is located here, they are not transferring any heat. So in a real chip, we are going to see that typically the sides have a very small surface area. So if the surface area becomes small, if we write Newton's law of cooling, we get Q equals HAS Ts minus T infinity, and if AS is very small, say it's 0.0001, then Q would be also very small. Q would tend to 0. So this is why if some surface is insulated or has very small surface area, we can actually neglect the amount of heat that is transferred from that surface. So since the question mentions it directly that we can consider those surfaces to be insulated, we don't actually have to look at these areas. But if you look at the picture of a real chip, we are going to find out that the side surfaces have very small surface area. So now let's solve this problem by making some assumptions. The first assumption we are going to make is that we are going to assume that this is a steady state problem. So this assumption is needed for us to actually use Newton's law of cooling. So this assumption is absolutely essential if we want to solve this problem. The second one is we are assuming negligible heat transfer from back and side surfaces. So this is given in the question. So I've already explained it. So we are going to move on to the next one. The third assumption we have made, it says that the chip is at uniform temperature. So this means that if you take any point on this chip, so for example this point or this or this or this or any point anywhere on this top surface, then all of them have the same uniform temperature. So if we do not make this assumption, then essentially we cannot say that the Ts in the Newton's law of cooling formula is actually a constant, and if that value changes, then we actually cannot use Newton's law of cooling to solve this problem. So that's why this assumption is essential. After that, we are making the assumption that we are neglecting the radiation and conduction heat transfer from this chip. So in real world, obviously there is going to be some radiation heat transfer and very little conduction heat transfer from the chip to the substrate, but we are neglecting them to better understand the heat convection process. And we know from our practical insight that the majority of heat that is transferred from this chip to the coolant is going to be due to convection because of the temperature difference, and also because the heat transfer coefficient values for both of these fluids, whether it's a air or whether it's a dielectric liquid, are very high. The fifth assumption is that we're assuming the thermal properties are constant. So this is pretty standard, as we have seen over several heat transfer problems, because unless the thermal properties are constant, we're pretty much powerless to use Fourier's law or Newton's law of cooling, which works for a steady state problem. So there is going to be one more assumption that is specifically needed for this problem, and this assumption goes like this. It says that all electric power generated by the chip is dissipated by convection to the coolant. So we know from the question's statement that there is a coolant that is flowing across the top surface, and it has a temperature of 15 degrees Celsius, which is also equal to the bulk fluid temperature T infinity for this heat convection problem. So we are assuming that all the heat that was generated when we operated this computer chip by passing some current through it, which give rise to Joule heating, all those heat is leaving this surface and going to this coolant. So every last bit of power generated by that chip is being dissipated from the top surface, and the coolant is receiving all this heat. So if that's the case, then we can solve this problem using Newton's law of cooling. If that were not to be the case, then we'd have to do a control volume analysis to figure out which kind of energy is going to which location, and from that we would also come to this same result. But for solving these problems, we can simply assume that, because we know there are basically these two things, and there is one surface and one moving fluid, which we are calling a coolant, and if the heat is leaving from the surface, it has to go to the coolant, because we are neglecting radiation and conduction heat transfer. So now we can actually write Newton's law of cooling and solve this problem. Since there are two coolants, one is air and the other one is the dielectric liquid itself, we have to use the Newton's law of cooling twice. So once for air and then again for the dielectric liquid. So for air we can write Q equals H, the surface area, times the surface temperature minus T infinity. So the question gave us the bulk fluid temperature, which is the coolant temperature, to be 15 degrees Celsius. It's marked here, but it does not specifically give us a surface temperature. All it says that the chip temperature must not exceed 85. So this means that at any location the chip must operate below 85, and we should design the chip for the worst case when it has reached 85. And since all other surfaces except for the top is transferring heat with the coolant or exchanging heat with the coolant, we know that the top surface has to be at 85. So after knowing this, then we can actually write the values in this equation. But before doing that, ideally I should put a subscript, because this is for air, so I'm writing air, and for H I'm also putting in a subscript of air. So I'm writing H air, which is 200. So I'm writing 200. The surface area is 25 over 10 to the power 6. So the 10 to the power 6 comes from conversion to SI. TS is 85, T infinity is 15, and if we calculate this, we are going to get 0.35 watts. So that's the amount of heat that is transferred from the chip to the coolant, and we have assumed, our sixth assumption was that all electric power which was generated is dissipated by convection. So this means this must be the maximum power that the chip was allowed to generate, because if we allow it to generate more heat, then the temperature of the chip must exceed 85 degrees Celsius. So that answers the first part of the question, and now we can simply repeat these steps for the dielectric liquid, which I am representing by a subscript of dl. I am writing HDL AS TS minus T infinity. So the dielectric liquid has a very high value of heat transfer coefficient, convection coefficient, and this is quite standard because from the theoretical video of heat convection we have seen that the value of heat convection coefficient is generally much higher for liquids compared to gases. The question did not explicitly mention whether you have forced convection or natural convection. Since this value is pretty high, we can assume that for both coolants actually there are forced convection going on, but for the purpose of solving this problem actually that information isn't necessary. So let's put the values and we get 3000 times 25 times 1 over 10 to the power 6 times 85 minus 15, and we again get something called 5.25 watts. So this is the answer, and we previously calculated another answer. So now what does this mean? So this means when we are using a dielectric liquid, the chip is losing 5.25 watts to the coolant. So when you are using the dielectric liquid which has a much higher convection coefficient, it's losing much more heat. So if you are using a liquid as a coolant, you are allowed to generate much more chip power at the same operating temperature, or you can actually allowed to like have some maybe flexibility to design your computer chip. So after solving this problem, we see that depending on what kind of fluid we are using, the convection coefficient is going to be different, and it's going to have an effect on the amount of heat that is transferred. So we can actually write this insight as follows: that air is a poor heat transfer fluid compared to liquids. So we can use this knowledge for solving many heat transfer problems or gain some preliminary insights that might give us some idea about how to solve a heat convection problem. So thank you for watching this video. Please check out my heat transfer playlists, and thank you again.